The system we are going to consider to demonstrate the design of a PID controller is very famous. It's taken from a Matlab page, precisely this Matlab page we are looking at now. In this page, they explain how to identify a real plant from experimental data. The plant is a lab equipment that I use to instruct control systems at the University Simón Bolívar in Venezuela. Its nickname was the hairdryer, still the hairdryer, and its real name is the Feedback Process Trainer PT326. This is the PT326. It consists of a fan that, through the opening we can see in the picture, blows air into the tube. We have also a heating element, which is actually a resistor that heats up the air at the entrance of the tube. Then we have the thermocouple. The thermocouple is used to sense the temperature along the tube. We can place the thermocouple at 3 different places along the tube. The thermocouple produces a voltage which is proportional to the real temperature. As we can see, it will take a time for any action in the heater to cause any effect in the temperature of the air located at a distance from the heating element. Now we are back on the MathWorks page. As I said before, in this page there is an example of how to use the identification toolbox to estimate some different systems. And here they use the experimental data from the PT326, and they find several models. Out of those models, I'm going to use one that I need to scroll down to find that model. This is the model we are going to use. And this model is the one I'm going to introduce in Matlab and do all my controller design using this model. So let's go back to Matlab and try to do that. I have already introduced that model, and we can see it by just typing GP. In this model, we can see the plant. We can see that there is a delay of 0.2 seconds, a delay that exists between sending a command to the actuator and see its effect in temperature at the thermocouple, and that's 0.2 seconds. And the transfer function is a second order function, as I said before, and it will be nice to see what are the stability margins of this transfer function, of this model. We can do that by just using the instruction margin from Matlab. Here we can see the body plots. Oh, let's wait for a second here. Okay, now we can see here the body plots of this model, and as you can see, it's very good. The gain margin is 10.7 dB. That means that I can increase the gain up to 10.7, and then the system becomes unstable, and which is good. The phase margin, it says here, is infinite. In reality, means that there is no crossover frequency, and never crosses 0. The magnitude is never 1, it's never 0 dB, and the phase at those low frequencies is around 0 degrees. So it's very good, and it's a very robust system. With this system, we shouldn't have any problem designing a controller. And another way to see how this system will work will be by looking at the step response in the closed loop. So imagine that I take just the plant and put a controller, which is just a gain, k equals 1, that's it, and close the loop and implement the controller in order to see more or less what will be the response of this system. And I can do that by using the step instruction of Matlab. Here is a response. As you can see, we can see an overshoot, typical of a second order system, and important thing to notice here is that probably the overshoot is no bigger than 17%. The time response is around maybe 0.5 seconds, and we can say also that after 1.6 seconds the system settles in its final value. That unfortunately this final value is not the step I commanded, it's not the reference I commanded, which was 1. There is a steady state error, and this is because there is no integrator in the loop, in the direct path of the loop, and therefore we cannot guarantee a 0 error for a step reference. But the system is very robust, stable in that respect, on the response, on the overshoot, and we should be fine designing a PID controller for this one. It shouldn't be that difficult. So the next step now will be to see how can we implement that PID controller. But before that, since the system gives us some degree of freedom, I'm going to add noise to this system, because in practice all the measurements have noise. So I would like to add some noise and see how the response of the system is with this noise. So let's go to Simulink and do that. We are now in Simulink with a small simulation of our hairdryer. Our hairdryer is here inside this box. We just simulated by a transport delay and a transfer function as described before, and our input will be a step of magnitude 1, and then we are going to add a noise at the output of this system to simulate the measurement noise that usually we get in real life when we measure physical variables. And then we can observe this noise. I selected noise with a variance of 0.001, and then we are going to see now what kind of output we get with this one. The simulation is already done. We can click here in this scope, and this is the output we observe, which is very noisy. We would like to mitigate this noise somehow in our control system or whatever we are going to do in order to make this less noisy. We just added the noise to make the problem a little bit more interesting. So the idea that we are going to do now is to design a filter to filter that output, and the output of that filter will be what we are going to feedback to implement our control system. So now the question is, how are we going to design this filter? And also this filter is going to change the open loop transfer function that before was just the hairdryer transfer function. After the filter will be the hairdryer times the filter, and that will change our open loop transfer function, and will change also our margins of stability, and we need to check that out. So that's why we need to design a filter that does not spoil too much the good things we got before, the good stability margins we got before. So let's do that, and for that we are going to go back to Matlab. So to have an idea of the filter we are going to design, let's go back to see the body plot of the original system. This is the body plot of the original system that we saw it before, and we like it, the stability margins of the system. Remember, the gain margin was 10.7 dB, phase margin infinite. So our filter shouldn't spoil too much this around, we will say, the medium range frequency, which is, I would say, is around 10.0. It's around 1 radian per second to 10 radian per second. And beyond that, everything is very bad. The phase goes very bad. We cannot do anything on this region. We can do something around this region between 1 radian per second and 10 radian per second. So the new filter we are going to introduce shouldn't affect this area from low frequency to this medium range frequency, and that's what we would like to do. So then we are going to design a second order filter whose cutoff frequency will be around 10 radian per second, and it will have complex poles with no resonance. Why we don't want resonance? Because we don't want any frequency to be amplified in this region. So, and selecting complex poles that allow that will be, I will say, will be good to mitigate the noise and not to spoil too much around this region, not to spoil too much the gain margin. If we can do that, then the filter could be used, and then we can proceed with the PID controller. I did a design already, and that's the filter GFN that I designed, and this is the filter. So as you can see, the natural frequency of this filter is 10, and that is our filter. So let's implement this filter in our Simulink system and see what happens. And now we did already, it's in here, and we can see the output in this scope. Since we ran the simulation already, we can just take a look at what we have here. As you can see, the output is smoother, it's still having variations, but that will be okay. And this is the output we are going to use to do the feedback. So the error will be the set point minus this signal. This will be our output, and directly to the PID controller. As you can see, we have changed the system. If we compare this with the previous, with this, I don't know what I'm doing this, let's cancel this. I just want to see here the scope. If we compare both solutions, the noisy signal and the filter one, well, we can see the improvement. But now that we have this filter, we like this filter, the idea is to see how, since the transfer function, the open loop transfer function has changed, we would like to see what happened to the stability margins when we include this new filter. And let's take a look at that. So we are here again on Matlab, and we can do that by using the instruction margin again. But remember, we use the instruction margin here, but now what we need to do is just to include the new transfer function. And here we go. We have the transfer function, the open loop transfer function, including the filter. Let's see how things went with this. As you can see, there was the gain margin has been reduced. We expected that. Before was 10.7, now it's 7.2 here. Before was 10.7 or something like that, now it's 7.2. So it has been reduced. Logically, had to be like that because we included 2 more poles in the system, but it didn't go that bad. 7.2 is still considered good gain margin. So the system will have a nice response with this gain margin. The phase margin was untouched, it's still infinite, because remember our condition, nothing here was going to be affected, and it wasn't. So with the inclusion of the new filter, so far this filter seems to be good. We are going to use it, and now with that filter and with this new open loop transfer function, we are going to design our PID controller. It would be nice to see the closed loop time response with the new open loop transfer function. In order to do that, we are going to use the step and feedback functions of Matlab. Okay, we have here the closed loop step responses of the two systems we are dealing with. The blue one is the original system, the hairdryer, the closed loop with the hairdryer, the normal and original hairdryer. The second one is the closed loop when we are using the hairdryer and a filter to reduce the noise. So we can see very clearly the effects of the filter in the closed loop response. We can tell immediately that when we included the filter, we made the system slower, as we can see here in the plot, because it takes longer to respond, and also it has bigger overshoot, and it takes longer to settle around its final value. As we can see, its behavior is more oscillatory than the first one, than the original system. So in order to see what happened, let's go back to the body plot of the system with the filter and compare with the original one to see to have the correlation between the open loop frequency response and closed loop time response. In order to find again the body plot, we are going to use the body function of Matlab. So we have here the body plot. Now with the two systems, we have the blue one is the original system with the hairdryer only, and then we have the red one, which is the hairdryer and the filter we introduced to reduce noise. Very quickly we can notice that the new system, it has more attenuation at the high frequency. This is good because this means it's going to reduce the high frequency noise, something we really want, and for that reason we designed the filter. That was the main reason, try to reduce the noise, especially at the high frequencies, and that was why we introduced the filter around 10 radians per second. And then that goal is achieved, we can see immediately here in the body. But when we look at the time response, we know that we have deteriorated the closed loop time response when we included the filter, and that was expected. But in order to see what happened here with the stability margins that determine the relative stability of the system, we need to have more resolution around this area. So let's do a zoom in in order to do that. Here we have a zooming around what we have called the medium range frequencies, and the first thing we can see immediately, and we know this already, is that the frequency at minus 180 degrees for the new system, the system with the filter, is smaller than the frequency of the original hairdryer. Because of this, the new closed loop with the filter, it has less bandwidth, and that means that it will respond slower, as we can see in the time response closed loop time response of the system with filter is responds slower. But also at that frequency we can check out the gain margin, and then the new system has a smaller gain margin than the original one. Because of this, we have more oscillations. The system is more oscillatory. We can see here with bigger overshoot, and his relative stability has worsened in comparison with the original one. So because of these reasons, so we have the new response which is worse than the first one. Now the question is, can we with a PID design with a new PID can improve, reduce the overshoot, make the system perhaps respond faster or with less oscillations, and to make it settle fast? Well, that's a challenge of designing this PID. But in order to see how to design the PID or have an appreciation of the design, let's take a look again of the body plot, especially the face of the new system, the red one, the system with a filter. So we can see that beyond perhaps 5 radians per second, when the phase is minus 180 degrees, the phase becomes too negative, and the lead that the PID can offer for that could be too little, or to compensate this very negative phase, it will be hard. So from this point on, I would say that the phase becomes too negative to really care about this range of frequency. By the frequency equals 8 radian per second, the phase is already too big. So we better stick around this area, and we can try at the beginning. We can try design a PID to have a crossover frequency of 5 radian per second. We are going to try to do that, but it's important to notice that we are expecting the PID to work on this area. That means when I say to work in this area, that means to get a crossover frequency, or the frequency where we get the phase of minus 180 degrees around this area. Beyond this point up, the PID probably won't compensate this. So then, before going to the design of the parameters of the PID, it would be good to have a review of the PID controller, to try to review what are the main features and characteristics of this controller. PID stands for Proportional Integral Derivative and refers to the 3 components of a PID controller. A PID controller has 3 parts, as we can see in the figure. These 3 parts are added to produce the controller output as expressed in this mathematical equation. The PID controller is well used in the industry. The theory of control advances produce more sophisticated and complex controllers, but the PID is still standing and is preferred in many industrial and practical applications. There is an intuitive understanding of the PID as follows. The proportional part is the reaction part. The action here depends on the current value of the error. It deals with the present. As long as the error is not 0 at the present, this action is on. It has the effect of reacting quickly to reduce the time response, but it can overreact. That is, it can become too sensitive and lead to instability. The integral action is an accumulation of the past error. The action here depends on the history of the error and is never erased. It deals with the past. As long as the error is not 0, the integral action keeps on accumulating to try to bring the error to 0. Integral action therefore tends to reduce the steady state error, but it can lead to instability if the accumulation persists, bringing the system to an unsafe nonlinear region. The derivative part measures the rate with which the error increases or decreases. For this reason, It's often said that it has a predictive effect. It deals with the future. This prediction allows taking action before the error increases or decreases too much, reducing oscillations. That is, it has a stabilizing effect, but it could be too sensitive to spurious changes like noise. Using the Laplace transform, we can find the transfer function of the PID controller. Notice that PID transfer function is not realizable. The order of the numerator is bigger than the order of the denominator. This is because pure derivative action does not exist in practice. An approximation can be obtained by approximating the derivative with a transfer function like this one, where Tf is a reasonably small time constant. The quantity Kp over Ti is known as the static gain. A high static gain value provides good tracking abilities for moving references, but it can lead to instability. We are going to design the PID controller using two functions I wrote here. We can see them here in the side panel of Matlab screen. And the first function is calculate PID PM, which means calculate the PID parameters based on phase margin specifications. The other function is calculate PID parameters based on gain margin specifications. So we are going to use, first we are going to use the calculate PID PM. And let's do it then here in Matlab. Here is the function, and I'm asking to find Kp, Ti, Td, and the transfer function of the PID controller based on the following specifications. I want a crossover frequency. I want a crossover frequency of 5 radian per second with a phase margin of 60 degrees. My open loop transfer function is Gp times GFN, which is the original hairdryer and the filter. And then I'm saying that I want Kp over Ti, the static gain of the PID, equals to. Then we are going to do this and let's see what's happening. Remember that we talked about 5 radians per second before, and let's see what's happening now. Here is the response, the closed loop step response for this system with that PID controller found with those specifications. As we can see, the system has a very bad time response, very oscillatory, and it takes a long time to settle, and that is not good. And what happened here? So let's try to do a zoom in this body. Here we can see that the body of magnitude is very flat around 0 dB. That's not good because it's not leaving the gain margin going down as we would like, even though we know that the phase margin is good, 60 degrees at 5 radians per second. That was the specifications. Those are the specifications we gave to the function, but we can see that the gain margin is 1.29 dB, is at 7.7 radians per second. So it's going too far. It's going to remember the around 8 radians per second here, and the gain margin is bad, and that's why we obtain this response that we are going to discard. We don't like it, and then let's try another specification. Probably this time we know that phi is very close to the zone that we concluded before, which is not good because the phase goes down very quickly. Then let's change this specification to just 2 radians per second and see what we obtain. The response is much better. just by changing the crossover frequency. Let's take a look at the body and zoom in. Now we can see that the specification is satisfied at 2 radians per second. We get the phase margin of 60 degrees, and now the gain margin is much better. It's 7.67 dB at 514 radians per second. And this is the response. Has an overshoot approximately of 10%, and it settles, we would say, maybe at 2.8 seconds, and this response is good. So let's save this PID controller to compare probably with another one. Now so far we have used the calculate PID based on phase margin. Now let's do the other function based on gain margin and see what we obtain with that one. This time we are asking for the parameters KP, TI, TD and the controller GPID based on gain margin specification. So what are we entering here to this function? We're asking that the frequency in which the phase is equals minus 180 degrees be 6 radians per second, and we're asking 8. We are asking for 8 dB as gain margin, and then we are introducing here the open loop transfer function that we know exactly what it is, and now we say the same thing. We need one KP over TI equals 2. So let's see what we get here. This is the response, which looks very good because it has no overshoot, and these are the specifications. The gain margin now is 8 dB at 6 radians per second as asked. These were the specifications. And now the phase margin is 66 degrees, which is good, at 1.95, almost 2 radians per second. And this response has no overshoot and settles, I believe, faster than the other one. Let's take a look. And yes, I believe that the PID we got with the gain margin specifications is better than this one. This one has no overshoot and it settles a little bit faster than this one. So we are going to select our PID controller, the one we found using the specifications given by the gain margin specification. So we can get rid of this one. We are going to use this PID. We are going to use this PID to do our simulations now. Before implementing the PID controller we have just found in a Simulink simulation, I would like to show the closed loop step responses of the new control system and the other two we saw before with the hairdryer by itself and the hairdryer and the filter without controller. Or in other words, the controller was just a gain equals 1. So let's do that because it's interesting to see that. So here in this instruction step of Matlab, we are doing the feedback of the GP only, the feedback of the hairdryer and the filter, and now the feedback with the new PID controller we found, the hairdryer and the filter. Let's see what this shows to us. Now we can see the yellow one, as immediately we can see, actually get to the reference. So because we expected, we put an integrator of the PID and that makes the error 0 in a steady state, which the other two don't have. So this is good. This is, in that way, this is superior to these two, but we knew that already. So let's take a look at the time response, at the how fast it responds. The yellow one, which is the control system with the PID, responds similarly to the red one, considering that the peak time is more or less the same, but it doesn't have that oscillation around the steady state value, and this is good. So we have improved by including the PID. We are making, first, we follow the reference, second, we do not have those many oscillations and settle quick, and third, we are immune to the noise because the filter most of the noise. And this is good. This is what we have achieved with the new PID controller. The blue one, which is just the hairdryer by itself, is still being, I would say, the fastest, but it has no remedy for the noise, so it's not worth it to consider that. So we have really found a good design for the PID that satisfies most of the requirements, and it is very good. Now we are going to try to see a simple simulation in Simulink. See, we have done here, what we have done here is that we had the hairdryer. Inside this hairdryer, I just put the noise again in here, and we have the filter outside. This is our implementation, and then we place our new PID controller. In this PID controller, if I open it, I have KP, the one you just found, KP over TI, and KP times TD as the constants P, I, and D. Now we need a filter to make the derivative realizable. And the coefficient for that, I picked the default 100. Is just adding a pole at 100 radian per second in this controller. And for that, oh no, there is a button here that says tune. Matlab has this PID controller which offer a way to tune the PID by just knowing to what is connected to, and it's very good. So I would like to use it to see what kind of PID controller this block PID will give us. So let's try it. Here we have it, and the block response, which is the PID controller we have found in this video, is the segmented line here, and the continuous, the solid line, is the one they propose, the tune response. Now, by looking at these two plots, I believe that the one we found here is better than that one, and first because even though the tune one is faster, but the difference is not too much, and we can see that by show parameters. Here we can see, for example, the rise time for this one is, for the tune one, is 0.347, and for the block, which is our PID, is 0.406 seconds. So the difference is not that much, and the our PID has better overshoot, and it has better settling time. It settles faster at 1.74 seconds. The difference is not much, but I believe that ours is offers more stability, because as you can see, oscillates less than the other one. And the tune one has this, even though the overshoot is not that big, but it has this undershoot, which is big. So definitely I prefer the one we found here, because this is a smaller undershoot, and it settles faster than than the one tuned by Matlab. So we keep ours. And we are going to try this little simulation here with a step of 5 and see what's happening. So we do that quickly. It's done very fast, and let's take a look at this is the voltage, the control voltage by the PID that we have found, and this is good. We see the variations, the going up and down around the reference because of the noise. But this is good, but this is not enough. To see a nice response of the output in a feedback system is good to see it, but it's not enough. We need to see other variables, and one of them is the output of the controller, because we need to see if the output of the controller is not too big, is not demanding too much from the physical devices we have. Then we take a look at this, and now we can see that the output of the controller is initially high, around 65 volts, and then it goes down to finally settle at some value. So yeah, initially it demands a lot, and that could be a problem when we do a real implementation of this. An actuator that can supply 70 volts maybe is not feasible. So we need to take a look at that, and we are going to, but this is to show you that the output of the closed loop feedback is not enough. We need to see the other interesting variables. One of them is the output of the controller, and also we need to do more interesting thing with the system, especially what is the response of the system to disturbances. That's another thing we need to see, but we are not going to do here, but we are going to take a more realistic simulation next to do that. We have here a more realistic simulation. We are assuming that we are going to implement our control system using a microcontroller or microprocessor, and for that reason we have included in the simulation an analog to digital converter, which will be these 3 blocks here, and then we discretize our continuous filter we found before, which is this block here. Our PID is also digital, so we discretize the continuous PID we found before, and also we added a digital to analog converter here. The digital analog converter and the analog to digital converter are both 10-bit converters, so we have a resolution of 1/1024. Also we include the saturation here. The saturation is something very realistic too, and we are saying that our actuator only can operate between an input voltage between 0 and 10 volts. 0 will correspond to 0 and 10 will correspond to 1024 in digital count. So we have done this to make it more realistic. Of course, we are using a design here that was designed using a continuous model in a continuous fashion, using the continuous methods to do the controller design. There are methods to do a digital PID controller, which is at the end will be very similar, but we skip that step, and we are going to assume that our sample rate will be enough for this system to try to work with our continuous design. And our sample rate is 100 samples per second, which means a sample time of 1/100th of a second. Now, what else? We also, very important to see is how to study, to analyze how the controller works when we introduce disturbances. So we added here a disturbance here, but this disturbance is not going to last all the time of the simulation, but only certain time. And for this reason, I have here two step functions. One step function, it comes at 5 seconds, and the other step function comes at 20 seconds. So we are going to do this. One of them will create the disturbance, the other one will cancel out the disturbance to take it to normal conditions again. So we are going to do this experiment. Here the diagram on the bottom is the same thing that we have on top, but just the controller is different. The implementation of the controller we found before is different here from this point, from this one over here. So let's take a look at the first simulation here on top and see what happens. So right now, the final this is from the previous simulation ID. I don't need this right now. Let's make disturbances 0. I don't want this right now. Disturbances are 0, so there are no disturbances. So the point is to see if everything we have done, all this non-linearity we have introduced, the discretization of all this, discretizing all of this, what all of that, what effects were created using by modifying the simulation before. So let's see if something has happened to our response by doing all of this. So let's run the simulation. And now let's take a look at here at the output. This is the thermocouple voltage, and it's very good. We can see the output is responds quickly, and also we haven't said that, but the reference is 5 volts. It goes to the reference, it responds quickly, and it settles. And this is the way this controller works. Now it would be nice also to see what was the output of the controller in this for this step. So this is the output of the controller. Probably we need here a little bit zoom. Let's move this a little bit here and then zoom it. Zoom in here at the beginning, because here we notice, I think we need even more. Here we notice that the first signal is a very big one. It's during the first sample. We can almost tell because there is a little thing here. It's very big. It's around 7,000 count. That cannot be implemented in the real life because only up to 1024 can be output legally. So, but this is the way this system works. However, it worked fine because it was just a little value for just one instant. So we have this. Now, what will happen if I include the disturbances? In this case, we are going to introduce a drop of temperature or more air coming to the fan, and I'm going to express that as a drop in this disturbance of -5. So that means that the controller has to even try to output more voltage to try to cover for that. It has to output voltage to get to the reference plus more voltage to compensate for this drop. But this drop is not going to last all the time. It's only going to last is few seconds, and that's why I introduced the other step, a final value 5, to cancel that. So let's see what happens. It's done. Let's see what was the output. Now we can see the output here. As you can see, the drop comes, and then the controller tries to recover, but remember, it's too much. It cannot go back to 5 volts, and right now at this point the actuator is completely saturated, giving the maximum. The maximum is 10 volts. With 10 volts we cannot get the we cannot compensate for that drop, and then there is an error here. And when the disturbance is off, then everything should come back normally, but there is a big transient here with a big overshoot, and then try to come back to the 5. At this point, yes, it gets 5 because the disturbance is gone. And the important thing here is why this transient here is not like this transient here, at least. Is worse, and there is an explanation for that, and the explanation is called Windup. Integrator Windup. At this point here, when the disturbance starts, the voltage that is needed to cover for that disturbance it cannot be provided by the controller or by the actuator, because the maximum is 10. We need more than 10 volts in order to compensate for that disturbance. But since we can offer 10 volts, there is an error. As we can see here, there is an error between the reference, which is 5, and here. And that error, because of the integrator, will keep on integrating, and there is this accumulation. This accumulation is called Windup, and it accumulates, and it will accumulate during the error. When this error is still there will be accumulation. If nothing happens here, this will continue this trend, and the longer it takes like this, the worse. So at this point, when the disturbance ends, we need to go back and go to try to recover our normal state and go back to our reference. But because of this accumulation, it takes long time. It takes all this time to get that to normal levels again. This is why this big overshoot and the transient we have here. This is the explanation for this transient. So we know that the actuator cannot offer more than 10 volts. The integrator doesn't know that, and it keeps on accumulating, trying to reduce the error. But the error cannot be reduced ever, and then this accumulation will keep on going as long as the disturbance is there. And this is called Windup. So, but there are methods to reduce this Windup or to eliminate it. So let's see what methods are those. Thank God, Matlab offers one of those methods. If we open the PID box here and we go to PID Advanced, Matlab offers to limit the output, and already I set the values here. 1024 maximum for this controller is 1024, and the lower is 0. And we are going to use an anti-windup method called back calculation. And this back calculation is based, if you go to the Matlab page about Windup, you will see the method they are using. And here, what's this method is based on is that there is a modeling of the saturation there. We told them that it's going from 0 to 1024, and there is an error here. Error between the real output of the controller and the input to this saturation. This error is going to be fed back using a constant KB, and when this value here is bigger than this, that is our case, when this is saturated, so this is going to be negative, and this is going to be negative here. What it's going to do is try to desaturate the integrator, try to bring it back, and that is going to do it. So we have a parameter here which is called KB here, and is the inverse of a time constant. The bigger KB is, the faster we are going to desaturate this integrator and try to take off all that excess that could be accumulating. And this method is explained in the book. This is based on a book, and the reference that Matlab put here is the book by Armstrong and Haglund, Advanced PID Controller. So in this book they suggest to select this value KB as I did here in the simulation. Let's see what I did that. And let's see what did I do in that case. So let's open this again. So they precisely recommend to that value starting with this, which is the inverse of the square root of Ti times Td. It's in other words, remember Kb, the inverse of Kb is a time constant. So we are saying that this time constant is between Ti and Td, and that's why the bigger Kb, in theory, the better, the faster we desaturate the integrator, because the shorter will be this time constant. So we did that, and let's see what is our exit now. So what is our output? So we did it, and then we open this, and now we see how the second transient here has improved, and that's good. It's almost similar to the first one. Before it used to be worse. But now if we take a look at this scope here, we see that the signal is saturated, but this is really not what I'm looking for. So this doesn't give me the information I need. Why? Because let's go back to the Matlab page. What the output of that scope over there, what Matlab is offering is the output here. But really I know that this is going to be saturated by this saturation that they put in here, this nonlinear saturation they put in here. I would really want to see the here before the saturation, because that would tell me so far what are the values before the saturation. It's going to be bigger than the saturation here, so it's going to get a steady state, and that can be determined by the block diagram here that we are not going to do now. So unfortunately this doesn't tell us the real accumulation of the integrator. This is just the output of the saturation. So this doesn't give us meaningful information. But the good thing is that we had improved the transient response thank you to that the anti-windup present in Matlab, based on the book of Armstrong, Advanced PID. Now let's take a look now at the other block diagram over here that I have on the bottom. So in conclusion, even with saturation, even with all this digital fashion, we have put everything here. Even with the quantizers that we have quantized everything and discretize everything, the control system is working, and even with the disturbances it recovers, it maintains with the wind-up, anti-wind-up, we have improved the transients considerably, and probably that disturbance was too big, but it was good to illustrate this example. Now what we have here is the same PID controller, but the implementation of the wind-up is based on another method. This method You can find it in the book Control System Design by Goodwin, Grape, and Salgado. They show another scheme to do the wind-up method that we can take a look at another time, but you can look this method in that book. So it's interesting to know what will be the response with this new method of anti-wind-up. In this case, we need also to place the disturbances. Okay, we did. And now let's run it again. Now let's take this is the result with a different wind-up method, and we see the same characteristic. The disturbance is too big. The system cannot recover. It produces the maximum it can produce, but there is an error. During this time the error is done, there should be if there is no wind up, should be an accumulation. But let's take a look, because there is a wind up, and now here you can see that there is no wind up, and unlike the previous one that we saw, this one wind up here, the previous one, this output here is the real thing. Why? Because since I did this block, I'm looking here. I'm not looking at the after the saturation, which is the one that goes to the DAC. I'm looking before the saturation. So before the saturation, something I cannot do with the other method here. Before the saturation, the output of the integrator or the output of the controller is completely level. It doesn't accumulate, which is good. It doesn't accumulate, so the integrator keeps on integrating, but there is no accumulation. It's keeping in a constant value. And why is keeping in a constant value? Because the input of that integrator is 0. The mechanism forces to be 0, and therefore it keeps the value, this final value here. And this makes the transient response very good. We can take a look here. Let's bring everything to view, and now we see here. Now let's try to compare the output of the second system with respect to the first one. I have it here, so we can compare the PID offered by Matlab and the method used by Matlab to get rid of the wind-up. And here, this is the method, the controller. This is another implementation of the controller with a different scheme of wind-up. I repeat, you can take a look at that in the book Control System Design by Goodwin, Grape, and Salgado. Here we can see both of them together. The blue one is the one on the bottom, and the yellow one is the one on the top. As you can see, the blue one responds faster than the one on the top. This method, it looks like it makes the system respond faster. Let's take a zoom of this to get a better appreciation. Here we can see it. So we can see how the blue one is really faster, and it settles faster. The other one, the yellow one, which is the one on top, is slower and takes longer time to arrive this. So it looks like the mechanism that is we are implementing on the second PID controller with the anti-windup mechanism. It takes better into account the information that it receives from the controller, and it produces a faster response. And but this only happens at the beginning. Well, what's going on here? Here we see. So here respond faster for the disturbances. Their behaviors are very similar. So it looks like we have found a good controller, robust to disturbances, to noise, because we place a filter and design the controller using the filter. We had a discrete implementation, as realistic as we could do it for this video. We implemented wind-up mechanism, 2 of them, and found out that one seems to give better response than the other one. But we need to experiment more with those 2. And I think we have achieved our goal in this video, and to try to illustrate the design of PID controller and about things that we really need to pay attention when we do these things. With the hardware in the loop, we could, for example, get our design and implement it in a target by transforming all this to code, the controller and in our digital implementation here. And even we could do a real-time simulation of all of this. But this is the first step. Always we do a simulation based on this PC, on the computer originally, and then we just move ahead trying to do a software in the loop or hardware in the loop. So this simulation, I believe, is very illustrative. It shows us. And thank you for watching this, and just subscribe to my channel and to see more videos like this. Thank you. Bye bye.